All right, welcome back, everybody. So this is going to be our last class before the final, which is on Thursday. So no crying. I know it's going to be sad today. Okay, keep your emotions to yourself. Can you do it? Yes? Come on. All right, we'll talk about the final at the end. We're going to have some time. I think we'll probably go for hour 15, hour 20, and then we'll come to an end, talk about the final, and you can go. All right. Last class, we were talking about simple interest. And I forced you to hang around so we could just at least talk a little bit about it before we actually get into it a little more today. And we actually got quite a ways through it. We talked about how when we compute interest, when you put money into a bank or when you borrow money from a bank, there's really two formulas that are used to compute the interest. One of them requires that you know how many times per year they're going to compound the interest, and that can be done, monthly, weekly, daily, and that will dictate what this number is. And then there's this other formula, which is called continuous compounding, where the n goes away. You don't have an n in the formula at all, but what appears in the formula is this e, and the e is a number, and it's a very special number. It's what we call the natural base, and this is what it's defined to be. It's called the natural exponent function. Well, the e is called the natural base, and it is approximately 2.7188 or 18281, blah, 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 and it's just like pi. It goes on forever. It doesn't have a pattern, never repeats. So it's an irrational number. And so what we want to make sure that we can do right now is get our calculators and find that button on our calculator so that we can evaluate e being raised to various powers, because in the formula, that's what this means. You're going to take e and raise it to some number. So if you have your calculators with you, let's try and figure out, first of all, what e is. And you should get on your calculator 2.718, blah, 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 blah. So I'm going to do it on mine. Blah, blah. Got it? 2.718. I'm just going to do that. Now you see if you can get your calculator to say 2.718. And if you can't, raise your hand. I'm going to come by and show you where it is. Okay? If you cannot, raise your hand and I shall come by. Okay. Let me see your calculator first. All these calculators are different. Okay, so you go ahead and bring up what you just had. You had e, and since it's just e, I want e to the first power. So put 1 and then close the parentheses, hit enter. There you go, okay? Who else needs help? E to the first power? Okay, you're working ahead. Okay, so the e you're using, where'd you get that e from? That's different than this e, which is right. Where's your natural log? Yes, that one. So what you want to do, okay, and then now look, it already puts it up there. What power do you want? And since it's just e, put 1, hit enter, 2.718. Got it? We're all good? We're good? Okay. So just complete the table. I'll do it also, and we'll verify everyone's getting the same thing. Something like 20.086. I'm going to round 3 decimal places. E to the 5th, 148.413. Ooh, e to the negative 5. 0.006. I'm going to go a little further. 738. Anyone have trouble getting the e to the negative 5? You got a different answer. Okay, so I need to see how you typed it in. Yeah, that e at the end moved the decimal. Yeah, same thing with yours. So remember what this means. It means move that decimal 1, 2, 3 places. Okay? You got it? You understand? Okay. Anyone else? What's e to the 0? 1. Was that your answer, or are you raising your hand? Okay, all right. Okay, so if we can use the E key, then we can apply the other formula. And this next example gives us kind of an insight into how we get different answers if we use different n values, and what happens if we do it continuously. And what we're going to see at the end is they're all pretty close to each other. All right, so you have $100, whoa, to invest for 12 years. Wow, okay. At 2%. How much would you have if using the following models? Okay. I'm not sure what they mean. How much would you have if you were using the following models? Do you think that's what they meant to say? How much would you have if you were using the following models? Simple interest. All right. Compounded yearly, compounded monthly, compounded weekly, compounded hourly, compounded continuously, and that's it. So look, scratch the first one because they don't give us an N there. All right. Let's do the part B. Annually, compounded yearly. So as soon as you see compounded and they give you anything other than continuously, that means you've got to figure out what N is. So yearly would mean N is what? N is always the number of times per year. So N would be 1. The fact that we're leaving it in for 12 years does not mean we make N 12. It's the times per year. It doesn't matter how many years it's going to be there for. So N is going to be 1. And we will use the first formula over there. So let's see if we can write that formula down over here. The amount will be P, which was the principal. That stood for the amount that you put in at the beginning. So how much are we putting in at the beginning? 100. And then 1 plus the rate. What's our rate? 0.02, always as a decimal. Good. Over N, which for us was 1, raised to the N, which was 1, times T, but T was 12, wasn't it? T is the number of years, and we're leaving it in for 12 years. Order of operations, what do I do first? What's in the parentheses? So do 0.02 divided by 1, which is just 0.02, right? Add 1 to that, and you should get 1.02 raised to the 12th power. Now on your calculator, do 1.02, raise it to the 12th, and you get a big old long decimal, right? 1.268241795. That's what mine says. And what I would recommend you do is just put as many decimals as your calculator shows. The more decimals you go, the more accurate you're going to be. So I'm going to go 1.268241795. Anybody have less than that on their calculator? Anyone have like just 1.268 or something like that? No? Everyone's goes out pretty far? Okay, then multiply that times 100. And that really, because of the way 100 behaves, it's just going to move the decimal point 2 places to the right. But if that number was something like 852, it wouldn't be so easy. You'd have to multiply it. So 126.82417. But this is money, and we can only go as far as the cents are concerned. So I'd say 126.82. And that's dollars, right? 126.82. So when you go to the bank 12 years later to crack open that nest egg that you've put in there, right? You've got 26 bucks more than you had when you started. Congratulations. It's probably with inflation worth less than $100 now. All right. That's what happens if it's compounded yearly. Now let's do it monthly. Let's see how the formula changes. Monthly means it's compounded how many times a year? 12. 12 months in a year, right? So 12. Just going to redo the entire formula we just did, replacing the n with 12. Everything else is the same. So A equals 100. 1 plus 0.02 divided by 12 this time, raised to the 12 times 12. So I'll highlight, this is the only thing that changed in the problem, right? The n down here and the n up here. So I've got to get on my calculator, I've got to do 0.02 divided by 12. And I get something like 0.0016666666 forever, right? Again, I would go as many decimal places as your calculator goes. Add 1 to that. So what would you get if you add 1 to that? You get 1.001666667. I believe that's what my calculator did. And I'm going to raise this to what power? 12 times 12, 144. So I'm going to raise that to the 144. Everyone know where their raise key is and stuff? So 100, and then what I'm getting is 1.270995,208. And then multiplying by 100, 127 point, we can round that, 10 cents. Not even an extra dollar, right? 28 cents more. High rollers here. We're high rollers, right? All right, what about weekly? What's n going to be if we do it weekly? 52. We'll say 52 weeks a year. A equals 100. 1 plus 0.02 divided by 52 raised to the 52 times 12. Again, the only thing that changed was the 52. Which is 100. All right, 0.02 divided by 52 and add 1. I have 1.000384615. I'm going to raise that to the 52 times 12, 624. No? You got something different? If you're good? Take that number to the 621st power. Yeah. Negative? 52 times 12. We're going to raise it to the 624th power. So you get 100 and then 1.271190494. Now we may be off a little bit, okay? So like if you're getting something different down here, you're getting like 4548 or something. That's okay. I mean, there's going to be little errors, but we should all be within a few cents of each other. So multiply, you get 127.12, I'll say, dollars. I didn't put the dollar symbol in front of it, but I think you all understand. So if the bank compounds the interest yearly, $126.82. They do it monthly, $127.10. They do it weekly, $127.12. It's not really looking like the more they do it, the better off it is for me. I mean, it is better off, but it's not significant, is it? And I tried to explain to you last time, it's because even though they're doing it every week, they're doing it on a smaller fraction of the money. So they take your money, they cut it into 52 pieces, give you just the interest on one piece, and they do that 52 times throughout the year. So it doesn't really accumulate the way you think it would. How about hourly? What the heck is N going to be hourly? Every hour they compute your interest. So first, let's figure out how many days are there in a year. 365, and 24 hours in a day, right? So 24 times 365, which is 8,760 on a non-leap year. That's right. If we're assuming N to be number of days to be 365. And let's go and do that. That's going to 100, 1 plus 0.02 times 8760 to the 8760 times 12. So 100, 1 point, how many zeros is that? 5 zeros, 1, 2, 3, 4, 5 zeros, 22831. We're raising that to the 105,120th power. Anybody having trouble getting these? Or need help on their calculator? No change, huh? So it's approximately $127.12, which was the same as doing it, what, weekly? I mean, now it is different. It's just that when it comes to cents, we're gonna stop looking at, you know, 0.12. After that, the difference doesn't matter to us anymore. So it looks like the more times they compound it, it converges to some number. And so that's where the continuous compounding comes from. The continuous compounding means we don't use that formula with N, we use this new formula. So let's do that one and let's see what the result is. I'm going to do this one right here. Okay, so the formula says I do P, which is 100, e to the, what's R? 0.02 times T, which is 12. See, again, there's no N in this at all. Now, order of operations says that I'm going to do, what's 0.02 times 12 first? Let's do that. 0.24. And so on your calculator now, don't do 100 times E. Do E to the 0.24 first. So E to the 0.24. And I just went around and made sure everyone knew how to do E on their calculator. So you're going to get 100 out front, and then that turns into times 1.27124915, which is basically $127.12. Now, would you agree that this formula right here is a little bit easier to do on your calculator than these? Just a little bit, because you just have to use the E key. And since it doesn't make a difference in terms of, you know, if we do it hourly or weekly or monthly, it's not that big of a difference. This is the one that is used most often, right? It's simple interest with continuously compounding the interest. We won't do the next one because it's just a repeat of everything we just did. But we'll do something a little more, I guess, interesting to us, right? Something we might find mind-boggling, I guess. Let's say you win the lottery, okay? All right? And not a huge lottery. Let's make it something reasonable. Well, a couple of million. Let's say a couple of million, all right? Let's say, well, no, I'm talking like the Mega Millions where they win, you know, it's like $450 million jackpot. I mean, at that point, doesn't really matter what you do, right? You can do whatever you want. But if you win $5 million in a lottery, are you set? You know, I mean, is that it? Are you set for life? Okay, so let's see. You win, I guess it depends on how you live, right? You win $5 million. Now let's say that's what you walk with, okay? Uncle Sam already took their 5, so you won 10, but you're only walking with 5, right? You win $5 million. You invest it in banks at, and let's go with the very low interest rate because you're not going to put your money at risk. You're going to throw it into an account. It's not going to give you much return. I'll do something like 1.8%. How much do you have after 1 year if continuously compounded interest? So, you know, let's change the problem a little bit. You really won 12 million. Uncle Sam came and took half. You had 6 million. You went out and you bought a bunch of shit. You're happy. You're set. The other 5 million is sitting in the bank. Okay? So you're like happy you got your car and your entertainment center and all that stuff you wanted, right? All right. So that's just sitting in the bank. We're going to leave it there for a year at that interest rate. We're going to see how much is there. All right? So what formula are we going to use? The PERT one, right? And so the amount that I should have should be equal to the amount that I'm putting in, my principal, 5 million, e to the r, 0.018, be careful there, times 1. So always be careful with that interest rate to move it over 2 places. 0.018. Yes, that's what you'll be for e to that power. So go ahead and do that. $5090814.82. 882, yeah, oops, 882. Come on, let's not be a penny pincher. You just won the lottery, okay? What does that mean? You made $90,000. That's right. Look, you didn't even have to work for that. That's $90,000 that you got to let the banks borrow your money, right? In 1 year, 90 grand a year. What's that? Yeah, the other guy who just, you know, said, you know what, I'm not going to spend this. I'm going to put this in the bank. I'm going to leave it there for 12 years. He had 26 bucks later, you know. But I mean, really, it's not necessarily that the more money you put in. How do I explain this? If you put in, instead of 5 million, you put in 500,000, how much would you make? 9,000 instead of 90,000. If you put in 50,000, how much would you make? 900. You see, so it is the relationship is completely linear, I guess you could say. But the thing is, you're putting so much in initially that it's going to return you a lot more. So even though you know, if you put in $500, yes, you will get the same ratio, I guess, of interest this person would, except that it's going to be like 9 cents instead of $90,000. So it's not, you know, 90 cents, whatever it is. So that's a pretty good situation to be in, right? Now think about the person who wins those mega millions, right? The people who, I mean, if you won 50 million and you invested this in banks, simple interest, you'd make $900,000 a year. You would have to put all your money in different banks because it's only insured up to 100,000. So you would invest it all over the place. You'd have all different banks, probably all over the world, and you have a bunch of people coming up to you saying, "You should invest in this thing I got here, man." Yeah. So I heard it's kind of a curse to be that, but I'd like to experience that. I'd like to see if it really is a curse, wouldn't you? Then you think about people like, you know, my first person came to mind is like Mark Cuban because he's a billionaire. A lot of people know, you know, billionaire. Now you throw, you know, this was 5 million, right? So throw another zero on there. You're at 50 million. So he's making 900,000 a year. Throw another zero. You're at 500 million. Now you're making 9 million a year. Throw another zero on there, so you're a billionaire. Now you're making what? Where am I? 90 million? 90 million a year off of interest alone? And that is a very low interest rate. The stock market, on average, the return in the stock market over time, I believe, is like 6 to 12%, but it's higher risk because you could lose it. You could lose on that too. But the stock market's pretty steady. So imagine if this was 6%, how that would change, right? Just change that E to, instead of 0.018, just change it to 0.05, 5%, which would be really bad with the stock market. 0.05 times 5 million. 256,000. 256,000. That's with 5 million at 5% instead of 1.8%. Now, the other side of this is where you get completely screwed with credit cards, right? Because credit cards, you borrow $5,000. They charge you an interest rate of not 1.8%, not 18%, like 27, 28%, right? Why? Why can they do that to you? Because you need the money. They know you need the money, right? Yeah. So, would y'all like to look at a scenario like that? Okay. You borrow how much? 5,000? We did something like this, didn't we? The TV one? No, I thought we did. We borrow 5K? At what rate? 25? That's low. That's low. You want to know after a year, or you want to go a couple of years? You want to do 3 years? Okay. So they have these deals. You know, you pay it off. You know, you have 18 months or something like that. Oh, let's do that. A lot of these things have 18 months, don't they? It's like 18 months, no interest, no payments, or no interest, minimum payment, and they are counting on you to screw up, aren't they? Why? Let's see why. So they're like 18 months, no interest, right? But after that, all the interest accumulates automatically, and you pay what you would have paid had you not had that rate. So 25%, 18 months, and you screwed up. So let's see how much you owe. So, and let's assume it's continuously compounded. It's 5,000 e to the, okay, what's R for us? 0.25, and what's T? Be careful with T. 18 months, it's measured in years though. 1.5. So always do the 0.25 times 1.5 first. We're about to throw up. Hold on. 0.375. You're not misreading your calculator. That's an additional $2,000. And if you look at the difference, 7274, let's say, minus 5,000. Okay, the difference here, the interest that you wind up paying, you pay $2,274 in interest after that 18 months is up. If you divide that by your original amount, 45%. So basically you're going to pay almost half of what you borrowed, half back in interest. Half back. I'm trying to teach my niece this. I told you all my niece is living with me. So she lost something. She lost something and she had to borrow something of mine to replace it. And I told her she could get it with interest. So I said, you can borrow it and pay me back in a month, and you'll owe me this plus interest, or you wait. Right? So I forgot what she did. I don't think she borrowed it. Never mind. Yeah, so she didn't want to pay the interest. So that's pretty startling, isn't it? I mean, I as a consumer, I always take advantage of those 18-month no interest things, because that's someone letting you borrow their money for free if you're disciplined enough to pay it back. And then that money at least is sitting in your bank and gaining something for you rather than it gaining something for someone else. But if you screw up, and they even have, like, if you miss a payment, right? Then you automatically default and you go to, you have to pay the interest. So you have to be real careful with those things. Yeah. But the thing is, it's not a con because it's the way we do business in America. Oh, cons stuff? I think that would be anywhere, though. I mean, most retail stores' credit cards are high percentages. I haven't seen under 18 in 5 years. Yeah, 24.5. Yep. All right, so you make your minimum monthly payments, you're going to be in trouble. All right, let's move on. Now, these formulas, and especially this one containing the PE to the RT, can also be applied to other situations where we want things to grow over time and that we want them to behave a certain way. So simple interest is one example. Another one is what we call exponential growth, and it's often used for modeling the way that bacteria grow. All right? So what I want you to do is look at this equation here, and I want you to see its similarity to the PERT. All right? The N is like the A. So the N is the number of bacteria that are going to be present, where for us it was the amount of money that'll be there after a certain amount of time. 25 is our P. That's our initial money in. Here, that would be the initial number of bacteria that you started with. For this particular example, they're saying a bacteria growth is modeled with this function. They're talking about a specific bacteria where it starts at 25. If it was a different bacteria, it might be 10. It just depends, all right? The E is the E. The R, instead of R, it's what? Can y'all tell what that is? It's K. And this is called, with bacteria growth, this is called the growth constant. But for us, it was our interest rate. So K and R are exactly the same thing. They control how fast it grows. And then T is time, and it's also measured in, well, let's see. In this particular model, it's what? Time is the time in minutes, okay? They would have to tell you how they want time to be measured. Okay, so let's answer this question. How many thousand bacteria would you have after 2 hours? If the growth rate is 1% per minute. Okay, so N equals 25. E to the K you're saying is what? 0.01, that's your growth constant. And then what is your time measured in minutes? 2 hours is 120 minutes. So you just have to be careful with those units. Hours here is what you're given, but the original formula was in minutes, right? So 2 hours is 120 minutes. So go ahead and see what you get. 25 E to the 0.01 times 1. What are you getting? 83? Approximately 83. Let's just say approximately 83. All right, we'll round it. Okay, so now, yeah, in thousands, right? So this would be 83,000 bacteria. All right, so this is what we call an exponential growth model. What we were doing over there was simple interest. Simple interest is an example of exponential growth. All right? Yes, but the number in front, the 25, will vary with the problem. So let's see if they have another one here we can look at. Now, these are just additional practice. Well, they use the same one here. It's 25. Yeah, they're using the same one. Scroll down. Let me see. Here we go. Yep. Well, this is a different problem. This is a drug problem. So this is perfect. This is perfect. It's hard to read that. Let's agree first. I'm looking at number 8. Is this in the homework? Or is this, no, practice? 5e to the negative 0.4h. So no, we do have some medical field people in here. Let's read through this first. The function d of h equals 5e to the negative 0.4h can be used to find the number of milligrams d of a certain drug that is in the patient's bloodstream h hours after the drug has been administered. How many milligrams will be present after 1 hour? Then how about after 6 hours? So you go and you take a drug intravenously or orally, however you take it, right? It's in your system. There's a high concentration of that drug in your system, and then your body does what it naturally does. It gets crap out of you, right? So slowly it starts to reduce the concentration. Yes? Okay. That's exactly what this is. That's exactly what this is. So this is the model that we have, right? And what we're going to do is try and figure out how much of this drug is going to be there. Now, this model is only for this specific drug. You go to a different drug, and what's going to change is the number in front and the growth constant will change. And they do the research before the drug comes out, and they figure out what that is going to be, and that way they know, okay, like ibuprofen, something that you take, but you're not supposed to take it again until so many hours later. That's because they know how it's going to drop off, right? Sure, yeah. It's a model. It's not perfect. It's a model. Oh yeah, there's lots of variables that are independent of this that will affect it, but we have to have something to go off of. So this is the most simple model we have, and we can always add more elements to the model to make it account for a person's, you know, height, weight, and, you know, different variables. All right, let's see if we can figure this out. How many milligrams will be there after 1 hour? Well, everything's in hours, right? That's what it said in the bloodstream, H hours. So they just want to know what happens when H is 1, right, initially? When H is 1? So that means they want D of 1, which means 5e to the negative 0.4 times 1. Anybody have that yet? Should be like 2 point something, or no. It's not 2 point something. Take that back. The final. 3.35 milligrams. mg, milligrams? Ah, okay. Got it? Everybody getting 3.35 on there? Okay, I have a question. In this problem, look, they said, okay, I'll ask it at the end. How about after 6 hours? That means you want to plug 6 in? D of 6, 5e to the negative 0.4 times 6. See what you get. Anybody? Yep. 0.45? Now here's a question they didn't ask, but I'm curious. How many milligrams of this drug were given to the person to start? 5? How are you getting 5? Where? Didn't say 5 anywhere, did it? Okay, so let's verify. It's correct. Okay, so you think this number here is the initial amount? That's right. Okay, so if H was 0, exactly, that's what I want everyone to see. If H is 0 in this model, that means you haven't started the clock, right? You're about to. You pop them in, and it's e to this whole thing is 0, isn't it? And isn't any number to the 0 1, we already said? So that's going to make this just 5. So this 5, like I said over here with our interest formula for money, the 5 was acting like the P, wasn't it? And that's the initial amount, the principal amount. So in this case, that number right there would be the initial dosage, 5 milligrams. An hour later, you still had 3.35 milligrams. 6 hours later, though, you've dropped down to 0.45 milligrams. That would be a good, you want to know? What? Okay, so let's talk about half-life since it's, you're interested in it. Let's see how you do it mathematically, all right? Okay, we'll figure out. So let's talk about this. We have to all understand what a half-life is before, because you obviously are familiar with it, and I'm not talking about the video game, right? Half-life. Okay, so look, different substances break down at different rates. Okay, so let's say this is a pill you take, and this is the full doses of medicine. In this particular case, it's 5 milligrams. With different medicines, it takes a different amount of time for half of it to go away, to get absorbed by the body and basically not be a factor in your bloodstream anymore. So the question is, how much time does it take for half of it to go away? How much time? That's called the half-life, because this is how much is left after that amount of time, right? Then, in the same amount of time, half of that will go away. And then in the same amount of time, half of that will go away. And then in the same amount of time, half of that goes away. And you keep going. And so, if that makes sense, it will never completely go away, right? I mean, you just keep half and half. But it gets down to a point that's not even really measurable anymore. So it doesn't matter. That's, again, it's a model. Theoretically, it never goes away, but we all know in the real world it becomes insignificant. That's right. That's right. Or that's how they, if they find a body, a dead body in a room, they measure the temperature of the room, and they measure the temperature of the body, and they assume it started at 98.6, and then they compute from there. It's called Newton's law of cooling, and they're able to determine a time of death. Yeah, I'm sure there's lots of little tips you have for us, aren't you? Got a lot? Okay, all right. Well, we'll do an extra credit project. All right. Okay, so how would we compute a half-life? All right. Think about it this way. We want to know the amount of time, don't we? Which in this particular problem would be h. H is our measurement in hours. So I want to know the left side, right? I know it takes 1 hour for there to be 3.35 milligrams. Is that half of 5? No. Half of 5 is what? 2.5. So I want to know this. To get the half-life, I want to know when the left side will be 2.5. And my right side, nothing changes. Do you see that? I leave hours blank because I don't know. That's what I would like to know. And I make this side half of 5. Right? Unfortunately now, you're trying to solve an equation, and the thing that you're trying to solve for is up here, isn't it? Stuck in an exponent? Yes? Can't. Nope. You can do square roots and things like that if the h you want or the variable is down on the bottom. Now, let me tell you what it is, and then I'll tell you how I did it. All right? So the first thing I would do is I would divide 5 on both sides. So 2.5 divided by 5, that's obviously going to be 0.5. Then e to the negative 0.4h. Oops, wrong one. Again, I'll tell you how I'm going to do this in a minute. The half-life, h, I'm solving it, I'm not telling you how, is 1.73. It's approximately h. And how you get from here to here is the big question. We've never in our lives, well, maybe in high school or something, we haven't, at least in this class, determined a way to solve for a variable when the variable is stuck up in the exponent. We don't know how to do that. But I'm telling you there's a way to do it, and you'll get 1.73. So what this means is that half of it goes away every 1.73 hours. So 1.73 hours, half of it's gone. 1.73 hours later, another half's gone. Another 1.73 hours later, another half is gone. And it keeps doing that until it's insignificant. So how do I go from there to there? You have to use logarithms. And we don't have enough time today to treat logarithms the way you have to treat them. It's usually Logarithms is a good, think about how many days did we miss? We missed the day my daughter was ill, and then the 4th of July. So we missed like 4 classes worth of lecture here. That's about what it would take, a good 2-week span to really get into the logs the right way. And it's just not worth us trying to force in here. So we're going to be kind of stuck. But would you like to see how to do it without any like just monkey see, monkey do how to do it on a calculator? It's very simple, okay? All you do right here, at this point right here, I'm going to give you a formula for this. H will be equal to the natural log, which is a key on your calculator, 0.5, divided by the negative 0.4. In other words, you're going to take this 0.5 over here, you're going to take the natural log of it, which is a key on your calculator, natural log of this, and once you get that answer, you divide it by whatever was up here. Just the number, and that'll tell you what H is. So if you natural log, not log, it's L and then an N, and then you put 0.5, close your parentheses, divide that by negative 0.4, and you should get 1.73. Tell me if you get it. Yay or nay? You got it? Yeah. Again, I can't explain why, and I can't even explain what the natural log is, other than to say it's a function, and it's a function that basically undoes this one, and it makes this thing fall out, and it's good. So the half-life is something we can talk about, but it's not something we can really get deep into. A lot of times you know the half-life of something, and so from that you can come up with this formula. The formula they gave you is usually determined from the drug manufacturer will tell you what the half-life is. Okay, now I'm going to do something else because this is so exciting for you. I'm going to draw a graph of the function that we were just talking about, all right? 5e to the negative 0.4h, right? So this is what's happening over time, right? As time goes on, let me change this to plot range. Negative 1 to 100. I don't know if you can see this, but right here there's a little dot. You all see that dot there? That's at time 0 how much of the drug is in the body. 5 milligrams, right? And then as time goes on, right, it drops off. And it becomes asymptotic, meaning that it gets smaller and smaller and smaller and smaller, right, as time goes on. Understand? Make this 50. Might be a little bit better. It still dropped pretty quick. Here we go. Okay, so what did we say the half-life was? 1.73? So if I go there, I don't know if you'll be able to see this, but at 1.73 time, it is exactly halfway gone. Yes? See that? Now, what's 1.73 times 2? So double that. What's 1.73 times 2? What is it? 3.66? 46, okay. So if I go there, now I'm here. And so, and remember, initially, half of it dropped. And then in the next 1.73 hours, half of what was there dropped. So you can see it drop from here to here. Understand? Okay. Now, the reason why I'm mentioning this to you is that the half-life of this particular drug was 1.73 hours. But depending on the drug or what you're studying, half-lives can be very different. So I'd like to do a little bit of research here. Has anyone here ever heard of Chernobyl? Chernobyl. I think I misspelled it. So what is Chernobyl? Nuclear disaster in Russia back in 1986, where you had a nuclear power plant had a meltdown of the core of the reactor melted down. They lost control of the nuclear reactions that create nuclear power. They lost control of it, and so the core got very, very hot, and it was a really, really bad situation. So what I'm looking for here is the type of radioactive material that was in that core. It's a certain type of radioactive material. So let me see if we have here. Well, you know, it was the first thing that came up. But I want Chernobyl type of type of reactor. That'll probably tell us what was in it. No. Type of what? Type of nuclear. But it's uranium. U-235, it looks like. Or is it 238? Chernobyl accident, blah, 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 blah. Well, let's just say it's, just for the sake of not having to sit here and search it, okay? There's a radioactive material that they use for the reaction that creates the energy, right? It's usually a uranium rods, and those are very radioactive. And radioactive materials are like microwaves, basically, or X-rays. But if they get to you, they basically go into your cells and they just alter your DNA, and then you just get all jacked up. You know, your cells don't know what to do anymore. They stop behaving like they're supposed to. So this particular type of uranium, I'm going to look it up, and again, I'm kind of guessing that it's to the U-235. I'm going to put the half-life of U-235 uranium. You want to do 228 or 238? Okay. 703.8 million years is the half-life of uranium-235. You see what I'm saying? So that drug, the 5 milligrams, you know, it took 1 hour and 73 minutes for half of it to decay. Uranium-235, 700 million years. 700 million years. Maybe 238's a little bit, okay. Half-life of 238, 4.5 billion years. Hey, who's counting, you know? What's that? It's just in that, you know, if you take a pound of it, right, then think of radioactive materials like a fire. You've ever been sitting around a campfire? You know, it gets real hot. Next day you go out there, no fire, you poke at it, you can still feel heat, starts to kind of deplete, and then eventually it's gone. Well, with the radioactive material, it starts out, it's a big hot fire. You know, 700 million years later, it's half of it is still fire, and then, you know, the next half of that, and so basically you're talking about it not going anywhere anytime soon, right? So Chernobyl, this city, Chernobyl, 1986, is still completely uninhabited. Nobody lives there. And the reason is because when it melted down, right here, when it melted down, it got so hot, its containment vessel was like trying to hold a a hot knife through butter. You've heard that before. This thing got so hot that even the things that were holding it in place, concrete, just right through. Okay, started melting down, started going down into the ground, and they knew they had this huge disaster. So what they did is they got volunteers. They said, you go in there, and they just filled it with concrete. They just poured concrete on top of it. And just, and most of the guys that went in there knew it was a one-way ticket pretty much, and they all got sick and died later. But that was the best way to contain it, was to just seal it in a coffin of lead. I mean, not lead, of concrete. And that would do the best to make sure the radiation didn't get out. So it's there, and this whole area is still uninhabited, and that was, 30 years ago or so? 40 years ago? Yeah. Mhm. Hmm. Yeah. Yeah. That sounds like a cute pet. I'm glowing in the dark javelina. Mhm. Yeah. Yeah. There's what I always thought was really fascinating. This is why I like to talk about this in a class like this, is that it's somewhat interesting. It's somewhat connected to what we're doing here. Half-lives of things like this. Remember our pill, 5 milligrams? Okay, half-life an hour, 73 or 1.73 hours, whatever it was. Here we already know the half-life is a long time. How many pounds of uranium did they lose control of that day? 10. That's it. 10 pounds. That's it. 10 pounds of uranium. That's amazing. It's you have to make it. Yeah. It's not a natural occurring element. And that's why, I'm not going to get into a political discussion here, but you have countries that are nuclear capable, right? Who have created or developed, they have the intelligence to create the uranium that you need to cause major problems. And so like countries like Iran, who are trying to develop the process, they're trying to get in place the process to create this type of uranium. If you want people to have that, then you always have the potential of it, getting into the wrong hands. And, again, I'm not going to get political, but there's a lot of bad stuff out there. The whole Cold War between the United States and the Soviet Union, all these missiles aimed at each other. And so what do you do with all that stuff? All those big bombs that were made and uranium all over the place, what do you do with it? Yeah, you could. What happens if you lose the ship on the way up? You know what I'm saying? So there was a project many years ago, and I haven't talked about this in a long time, so I don't know how accurate this information is. But when you make uranium, when you make the bad uranium, I only call it bad because it doesn't go away and it kills people, okay? But when you make it, there's a lot of byproducts. You have a lot of the water that you use to cool these things, it becomes bad water too. So you got this like soup. They've got these huge vats of soup that are used to contain this bad soup water, right? And I'm talking about, you've seen these water towers like out on the side of the road, these big water containers. They've got some back from the 1950s that they built that are made out of concrete, and they've got this soup in there. They really don't even know what it is exactly that's in there, like the makeup of it, because it was just like, hey, we got all this extra stuff poured in there. And but what I've heard or read about this is this stuff is so bad that if you took just like 1 cup of it and you set it in this room, and just we sat in here through our class and then left, like we would probably all be dead within 6 months. Like it's that bad just from being around that little soup, that little cup of water. So they've got this like, thousands and thousands and thousands of gallons of this. And so what they decided was the best way to contain this, because these concrete things are only going to last so long, and they're vulnerable to attack and things like that. So what they wanted to do was take this liquid and convert it to a solid. And, because if you ever spill, you spill something like a cup of water, it's hard to pick up, but if you spill an ice cube, it's much easier. So they want to convert it to a solid. So they were going to build this refinery. Okay, here's my little refinery, and they were going to take this in here and make a solid. Once they got it to a solid, they were going to put it on a train. They were going to take it from the train. They were going to put it into the middle of a mountain. So they're going to find a mountain that was geologically stable, something that wouldn't have to worry about it moving around for the next, 50,000 years. Stick all our bad crap in there, shut it, and leave, right? We do. We do have places that are perfectly suited for that. The problem with this was that in the process of converting from liquid to solid, it created gas. And the gas turned out to be just as lethal as the liquid, and gas you can't contain at all. So this whole thing kind of went away. I don't know what the status of this is, but the thing that most concerned me when I used to talk to my students about this, because I told you I haven't taught 1314 in a long time, and I like to get into this because we can kind of have time to do this. This is our last math class, right? Okay, ever. So, what about the Soviet Union, who was in the same arms race as we were? Since then, they have fallen apart, and they've got all sorts of stuff all over the place, and there's no real control over it the way that, at least in the United States, there's some sense of where it is and who's got access to it. And I even saw some documentaries on people that would go to the former Soviet Union, go into the forest somewhere with these little, what are they called? Geigermeter? Yeah, and the thing that picks up radioactive radiation. And it's like, whatever, and they walk around and they'd look for it, they'd find it, and these guys are running with these big old tongs, and they would pick up this thing, and they would run, and there'd be someone, like their partner would be watching them on a radio and be timing them, and then would like hit a horn and be like, as soon as they hit the horn, they'd drop it and run. Like they could only be exposed to it for a certain amount of time. And they would just like slowly, like one person at a time, bring it closer and closer, and then dump it into some, containment thing. And, that's always been my fear, is people who can get their hands on that stuff. Because it's not, the stuff, these byproducts aren't going to be a mushroom cloud, cities gone like Hiroshima, but it's enough to cause a major, major problem, What's it? Yeah, exactly. I mean, if someone had access to, 10 gallons of this soup, you could cause some chaos. So that's always been my big concern, is the accountability for this sort of thing. Oh my gosh. Okay. Yeah. Well, again, we're not going to get political. We're just going to talk about the facts. As far as I know, what I've told you is pretty accurate. What I do know is Chernobyl is still shut down. No one's there. And it's all because of this exponential decay model that shows that the half-life of uranium is so long, it's not going anywhere anytime soon. No one's going to be around there anytime soon. Mhm. Yeah. I mean, it's a fire. It's not going out anytime soon. So, and when you think about millions of years relative to like our existence, at least our modern civilization, it's not much, Anyway, are we excited now? This is exciting, right? Makes you want to go run around with flowers and tell everyone love and peace, right? All right, so how much more can we handle? Let me tell you from this homework here, because now at this point, the notes get into talking about inverse functions. From inverse functions, we get into logarithms, and then we start doing solving with logs. And again, I think this would take too much for us. So I think I'm happy. If you can do some simple interest problems, a couple of these bacteria problems, that's good with me. Yeah? Yeah. well, no, I mean on the test, I'm saying from today. So let me talk about this homework and just show you off this homework what I think you should be able to do. So I'm looking off of page, it looks like the interesting stuff gets going around page 14. Page what? 13? No. 13. So we're going to look at page 14. These are problems you should do for homework, and these are also problems that you should do to prepare for the final. Number 11, interest. How long will it take for this investment to grow to 10,000? There's a hint on this problem, all right? You start with, oh, wait a minute, hold on. Ooh, no, this is not good. No, hold on. Where's the homework assignment that goes with all that other stuff? Hold on, did I skip over it? Yes, I did. You don't want that. See, they were already using the logarithms there. Back up. There's no other? Yeah, we'll do the additional practice ones, but yeah, those look like they'll do. Okay, so scratch what I said. We're going off of page 4. Page 4, number 1, very similar to what we did in class. 100, I think we used, it was 100, but it was 2 was it 2%? This is 2.4. Here's a bacteria problem. Number 2. Number 2. Number 3. Number 5. An investment property in 1997 was $250,000. If it increased in value at a rate of 12% per year, what is it worth in 2005? So you have to figure out, what's the rate, 12%, what's time, so how many years? 8 years. And we're going to assume the interest is compounded continuously here. All right. Just use PERT. Yep. Nope, N would not be used here. It doesn't say, right? Compounded. Yeah. It doesn't say how many times it's compounded. So if it doesn't say how many times it's compounded, we're assuming it's continuous. I like 6. George is trying to decide which loan is better. Both lending institutions offer loans based on continuous compounding. First one offers a 5-year loan at a certain rate, the other one a 4-year loan at a different rate. George wants the loan that will result in the lowest total payment. If he's borrowing $3,000, what should he take a loan on? Well, but it's a different rate. Well, you have to be sure of that. You have to compute it. You can't assume that the longer one's going to be necessarily less. Because you could make it, you could mess with the rates enough to make it work the other way around. Oh, the amount of plutonium remaining in 1 kilogram after X years is given by this formula. There we go. I hope we can all read that. I can barely read it. What does that say? 24,360? 24,360? So negative X divided by 24,360. And then we did 8 already, but I thought 8 was a good one. And that's about it. So I think 1 through 8, right, off of that, I mean, the whole thing would be fine. Now, what else on the final, what else are we going to have? Let's talk about that. That's going to be from test packet 2. And it's just going to be the stuff at the end that we did not get to on the last test. So remember, well, no, it was a little bit further up than this. Yeah, even, odd, right? That's what we were tested on last time. So I think all of these examples, this example where I give you a function, you determine the leading coefficient. So I'm gonna highlight these. I'm gonna highlight them in blue here. Page 51. Yep. Page 51. Example 1. Example 2. So if you remember on these, when it's already factored for you, it's one advantage, but then there's also some drawbacks when it's already factored. This one's already factored, so I would definitely anticipate me giving you something that's factored already and having you go through this sort of thing. I just may not give it to you on the test in that format where it's a table. I just may say, what are the zeros? Do you cross or do you bounce? Draw a picture. And then the leading coefficient test. I will definitely ask you about this. Something like this, remember it's not factored, right? But you're given the zeros. And so from the zeros, you create the factors, and then you draw it. You have to just go back and look at your notes, but so far all these examples are great. 4 is good. I like 5 because in 5 we had to factor that, right? That was the first one where I did not give you the zeros. So you had to go through the process of factoring it. I believe we did it on a different page and we came back and put it in here. So example 5. Example 6 worked the same way. I think that's a good one. I'm not going to give you that many on the test. I would say I'd probably give you like maybe 3 at the most of these. But be familiar with all these different types. And that's it for the polynomials. After that, we had the rational functions. Are there any questions on that? We didn't even have to graph these, did we? Those formulas? P and the Q. I think I know what you're talking about. This right here? Well, you don't really need that. Here's what you need to know, and you won't. We'll just do a sheet again like we did last time, where you can just write down some notes. All right, just one side though, and just as long as you don't have any worked out problems, just some stuff to reference. Things like, if you're going to try and find the x-intercepts of a rational function, what do you do? If you're trying to find the x-intercepts, set the top to 0. If you're trying to find the vertical asymptotes, you set the bottom to 0. Yep. Yep. In the denominator. So I like these problems that were on page 60. Right here. Because for each of those problems, we found the vertical asymptotes. But we also found the intercepts, the x and y intercepts. And that's something I want you to be able to do for a rational function. Find x-intercepts, y-intercepts, and vertical asymptotes. I think that's what I am looking at, right? Yeah. These, did we find intercepts? Oh, we did, yes, okay. And domain. So those are also good. These just weren't quite as robust as the ones before. And then this one application, that just was, can you interpret what they're asking? They give you a function. Yeah, the sunflowers. And that's it. So big picture, polynomials, know how to sketch them, which means you have to know how to find, left and right behavior. You have to know the x-intercepts and if you bounce across, and then you draw it. For rational functions, just be able to identify vertical asymptotes, x-intercepts, y-intercepts, right? Domain. And then maybe an application of that. And then when we get to the next simple interest, both formulas, bacteria, some decay, the plutonium thing that we had. That's pretty much it. Now, we didn't miss a test, or we did miss a test? We did, right? So we need to discuss how we're going to do this. And I talked to a few of you about this, I believe, right? Did I talk to anyone about this, how we're going to do it? Okay, so let's all agree on this so that we're all comfortable. Silly bus. Oh, this is the wrong class. Bless you. Is this it? This is us, right? All right. So we're supposed to have a homework grade, 10%. Quizzes, 15%. Exams 1, exam 2, exam 3, and then a final, which was 25%. These 3 exams were 50% total, right? So what's 50 divided by 3? Someone give me the decimal for that. Just to make sure I've got the right thing. What is that? 16. See, it's not a nice number. I'll just say, we'll round it. We'll say 16.6. All right, so here's the deal. We've got an exam 1 grade, an exam 2 grade, exam 1, exam 2, and a quiz, right? We have those grades. Homework, I did a homework check, right? I did one homework check at the midway point. We'll do another homework check at the end, right? It'll be like I did last time, just go through on Thursday. Just bring your homework with you. I'm just looking again for effort. Okay, so we will have a homework grade. Now, the question is what to do about this. So here's my view on it. If you come in and take the final, and your final is better than both of your exam 1 and 2 grades, then I'll count your final grade here and here. Understand? Which will be good, because that means the final will be, what, almost 40% of your grade? But if you come in, your final is lower than one of these 2 exams, then I will count whichever one is higher, I will count for your 3rd exam. Understand? Would the final of this last test will still be 25? Well, it'll depend on a student. So look, let's say I have a student that on exam 1, they got a 72. On exam 2, they got a 65. Exam 3, we don't have a score for, right? And then on the final, let's say they come in, they do 78. That means I'll make their exam 3 score 78. But if I have a student who did 72, 65, they come in on the final and they get a 68, then what I'm going to do is I'm going to replace this with what? 72.
But still, the lowest grade, or the low grade, the 68, still counts 25% of your grade, yes?
Yes.
Okay.
Yes, but that's better for you in this case because that it's only 25%, as opposed to over here where now it's, now imagine if I said, no, it's just, your final is going to replace your exam 3. That means your final is now 40-something%, right? 41, 42% of your grade. That's a high stakes exam. This way there's some flexibility. If you don't do as well as you wanted to, then your other exams will help you.
So what if, just to be fair, for everybody, if it's easier for you to do the same thing for everyone, whatever the highest test grade is, use that for the final, and then make whatever the lowest test grade is be for the exam 3?
No.
No?
It's not a matter of it being easier, because there, what that's going to do is that's going to, let's say you got a 72 here, now that 72 is going to be 25% of your grade, right? It's not hard for me to figure out which one's higher and replace. I do all the grades in Excel and then I just put them into Canvas later, so I just have it pick the low and the high.
So the quizzes, we only really had 3, is that correct?
We didn't have many. 4, but I did some attendance one. I haven't put all of them in. I don't want to bring up grades because it'll show everyone's grades. Yeah, but I have to go through and at least drop at least one because I told you I would drop at least one. The quiz, yeah. Yeah, so, yeah. Oh, yeah, I graded those and put those through, sorry. Here you go. Yeah, I wound up getting those graded that same night. Are we good? Do we have any other questions? It's our normal class, and when you're done, you're free to go. And